Okay, this is part 2 of non-horizontal projectile motion. And I'm going to do a little problem over here, and this is a problem of something getting launched at an angle. Now notice what happens here is upon launch it's got both an x and a y component, so we can no longer say it's strictly horizontal motion. It's got an upward component to it because it's going up upon launch instead of just going out straight. See, before, when we did things like a ball, let's say here, rolling off a table, when it started the motion, and as soon as it left the table, right here, its velocity just had an x component. It wasn't going up or down. All right, so we said it was just horizontal. Here, though, the object, ball, whatever it is going to be, has got an initial component in the y direction. So let's see what we want to do. What we want to do is we want to find out what is the final velocity right here where it hits, and we want to, let's say we want the range, so we want to know how far from here to where it hits over here. We'll call that the range. And of course, if this is my x direction, then the range is going to be the displacement in the x direction. In other words, this is my final x position, this is my initial x position. The difference between this position here and this position right here is this change in x. Okay? So when we want to solve this problem, what we have to do, first thing we want to do is get the components for our initial launch vector. This is my initial vector here. And so what I want to do is, well, let's see, I'm going to, just so that you can see this, I'm going to make a little grid over here, a little coordinate axis. All right, in yellow. Now what's my initial component in the x direction? You can stop the video now and see if you can calculate for me the initial component in the x direction and the initial component in the y direction. Okay, you're back. So here's what hopefully you did. Hopefully you went, and I'm going to do it in light blue here, and you drew in your box, and you did a little box down there, and you said, okay, this guy here, oh, let's say, get rid of that. This guy right here is my x component. And so what's my x component? The x component is going to be 5, because that's what my resultant is, or that's the velocity that's being launched up at 10 degrees. 5 times the cosine of 10 degrees. And that's this vector right here. That's my x component. My y component is going to be here, and that is going to be 5, hopefully you got this, sine of 10 degrees. Okay, so from this we know that the initial velocity in the x direction is 5 cos 10. The initial velocity in the y direction is 5 sine 10 degrees. And if I do that, might as well do that now. Let's just see on my calculator. 5 cos 10 is going to give me 4.9. So this is going to be 4.9 meters per second. This one is going to be, oh wait, 5 sine of 10, 0.87. This one's going to be 0.87 meters per second. Is that right? Yeah. All right, so now we have our initial velocity in the x direction, initial velocity in the y direction. Now what we need to do is to find out what my final velocity in the y direction and my final velocity in the x direction is going to be. This is my final velocity, Vx, let's say final, and this is Vy final. So how am I going to calculate that? Well, we know that the velocity in the x direction never changes. So the final velocity in the x direction is the same as it started, and that's going to be 4.9 meters per second. The final velocity in the y direction has to be calculated as the initial velocity in the y direction plus the acceleration in the y direction times the time. You can also notice that if we're on a level path here and this doesn't change, that just like we talked about before when we had your hand throwing up a ball and the ball went straight up and came straight down, that whatever your initial velocity was going up was exactly the same in magnitude coming down, just the opposite side. So that's the case over here with something going up and down, and it doesn't really matter that it's got an x component because we treat these x and y components independently. So we can notice immediately that V final, Vy final is going to be negative 0.87 meters per second. If we didn't know that, we would have to calculate it. And we can calculate it in this fashion. We look at the change in y as the initial velocity times time plus 1/2 a t squared. We know that the initial velocity is going to be 0.87 times time plus 1/2 negative 9.8 t squared. So we can factor out a t, 0.87 minus 4.9 t. And now what we're interested in is this is the change in the vertical position. Well, if we go start on the ground, that's my starting position right on the ground, I go up and I come back down to the ground, then I didn't really change position vertically. I changed position horizontally, but as far as vertical is concerned, this direction up and down, I didn't change at all. So this change in y here would be 0. Okay? Now we would find that time is equal to 0, or 0.87 minus 4.9 t equals 0 to solve this equation right there. So time can't be 0 because it takes some time to go across. So this is what we're looking at, and time is going to be then equal, solving this equation, 0.87 divided by 4.9, and that's going to be 0.87 divided by 4.9 is going to be 0.178, so 0.18. 0.18 seconds. Okay, so that time is how long it takes to go from this point position here to this position here. That's the time. So our range, delta x, then, is going to be the initial velocity in the x times time. which is the initial velocity in the x is 4.9, which is this one here, times 0.18 seconds. So this is going to be the range, and that is going to be that's going to be 0.88 meters. 0.88 meters. So what is the final velocity then? Well, final velocity is this velocity right here. Let me do that in yellow now. This right here is what my final velocity is going to be. It's going to be a result of this x component and this y component. So the x component is going to be just this, because that never changes, which is the 4.9. So this is going to be 4.9. The y component here is going to be the exact opposite of what we started here, because we did not change any position. And actually I should have showed you something else there, but this y component here is going to be 0.87. See, at the start it was 0.87 heading upward. Now at the finish it's going to be 0.87 coming back down. So the final then velocity here, v, is going to be gotten by taking the Pythagorean theorem for this, and we're going to say v then will be the square root of 4.9 squared plus 0.87 squared. And that will be 4.9 squared plus 0.87 squared, square root of all of that, 4.977, so it's about 5 meters per second. So this is 4.9 meters per second. In magnitude, its direction here, which is close to 5. And notice something, I want to just show you something. See this here? It's very, very close to 5 because it's 0.977 actually. We did some rounding when we were doing calculations, but you would expect it would be exactly the same. As it launches, it's 5 going up, so this is going to be 5 when it hits. We just proved that. What about this angle here? This angle is going to equal to the inverse tangent of the opposite, which is this side, over the adjacent, which is this side. So it's this side is 0.87 divided by 4.9. And that angle should be inverse tangent of 0.87 divided by, that's 10 degrees. So we just proved something. That we go up at 10, and look at that. We come down at the same speed we're going up, the same angle, downward only. So we'll do some more problems in the next video.